Welcome to the final Science and Statistics lesson, but remember there is a live workshop coming up after this lesson where you'll be able to ask questions, and I'll give you lots of practice questions so you're ready for the exam. This final lesson is on statistical power. There are the learning outcomes. Off we go. Bit of a recap from the last lesson to make sure everyone's on the same page. We looked at a statistical inferential decision-making process, working out p-values to see how likely it was that our sample mean, because we only get one sample mean from any given study, how likely it was our sample mean came from a distribution where nothing was happening. And if that p-value was big, then we retained the null, and if that p-value was small, then we rejected it. We understood the properties of the sampling distribution because sampling distributions tend to be normal, and we know the properties of normal distributions. It gets a little bit fiddly in second year. You'll have to look at the assumptions you're making and test the assumptions. Good statistical software packages test your assumptions for you, but for first year, sampling distributions are normal. Sampling distributions have particular properties. And just to put the little sample means in there for you, you can see that if nothing is happening and the null is true, most sample means will be around the population mean and we'll retain the null. But every now and again, we'll get a sample mean by chance alone that is very far away from that population mean. Those are the red ones. And we'll end up rejecting our null hypothesis less than 5% of the time. You can see the inferences drawn there. Sample means probably came from a population where there was no effect. Sample means probably did not come from a population where there was no effect. I'm going to move now exclusively to these curve type distributions, but they're much the same. They're sampling distributions. And I'm going to use dotted lines for hypothesized null distributions and red lines for the actual distributions, which is something I haven't kind of mentioned up until now. When the null is actually true, these two things are on top of each other. And I hopefully didn't draw it perfectly good. So you can see one's on top of the other. It's not completely covering it. That's what I wanted. When the null is true, the hypothesized null distribution is exactly the same as the actual distribution. That's what it looks like. And when that's the case, this is what I kind of showed you a bit more crudely on the earlier slide, you can see that you've got these areas of retention and areas of rejection. The areas add up to 5% if we have a p-value cutoff of 0.05. That means there's a 5% chance of rejecting the null hypothesis when it's true. So that's an error. So there's a 5, and it's called a type 1 error. It's a specific type of error. There's a 5% chance of rejecting a null hypothesis when it's true. Well, that's a type 1 error. Okay. Now, the other shorthand I'm going to do to make these diagrams a little less complex is, yes, for a two-tailed test, you don't even need to know what that is, but for a two-tailed test, you've got two regions of rejection. I'm just going to lose the one on the left completely to make things simple. What I want to focus on, though, is this idea of the type 1 error, 5% chance of rejecting a null that's true. So if we set the type 1 error rate at 5% of the time when the null is true, we'll make an error and reject it. So why don't we set it at 5%? Why don't we set the type 1 error rate at 1%? Or 0.1%? Or 0. Let's make it 0. Why don't we do that? And then we won't make any type 1 errors, or type 1 errors will be very, very unlikely. Why don't we do that? Well, unfortunately, there's more than one kind of error that's possible here. And from what I mentioned at the very end of lesson 5, you might get a sense of what it's going to be. You see, the type 1 error, pardon me, is the probability of rejecting a true null. But there's something called a type 2 error. And so beta and alpha, not necessary. If I mention either of these in the exam, I'll mention both. But usually type 1, type 2 error. Type 1 error alpha, type 2 error beta. Type 2 error beta is the probability of retaining a false null. And I kind of alluded to this at the end of lesson 6 when I kept saying things like, well, science is a balancing act, and we want to avoid both these errors. That's exactly what I was talking about. So let's kind of drop the left-hand side and just focus on what, just for simplicity, and consider that this is our little type 1 error here. And you can see we've got to now consider this other possibility. The top one, the dotted line, the hypothesized distribution, is in the same place as the actual distribution because the null is true. See up here, null is true. That's why the red line and the dotted line are in the same place. When the null is false, they're in different places. This is the null distribution. This is what's actually going on. So we've just been considering this little region of rejection here, this 5%, which is a type 1 error. And indeed it is, but this huge red bit down here is a type 2 error. Now when the null is false and we retain the null, we're retaining a false null. That's bad. That's a type 2 error. We've made an error. And you can see the relationship between these two errors. It's a trade-off. As one gets bigger, the other one gets smaller. Okay? You can't have it both ways. I'm getting confused now what slide I'm on, but let me go through that slowly. This would be our standard decision rule. Reject the null if p is less than 0.05, right? That's what it looks like. Let's say we become more liberal, okay? We reject the null if p is less than 0.2. Our type 1 error is blown out to 0.2. Wow. So 20% of the time when nothing's happening and the null is true, we're going to reject the null. This is why it's described as more liberal. Jumping at shadows, squeaky floorboards are ghosts, and teeny tiny differences are ruled significant. You know, that's not desirable at all. But look what happens to our type 2 error. It gets very, very small because the probability of retaining a null that's false has dropped. Okay, let's go back to 0.05. Now let's become ultra conservative, you know. Here, our type 1 error is tiny. The probability of rejecting the null when it's true is very, very small. But our type 2 error is catastrophically high. This would be like someone waiting until Lismore was underwater. No, this would be like someone waiting until the water's up to above the opera house before saying, oh yeah, maybe there is something to this climate change. Conservative is bad. Being conservative means that you're rarely going to say something's happening when it's not, but you're also going to miss out on saying something is happening when it most definitely is. So understand the trade-off between these two errors. Type 1 error, probability of rejecting a true null. Type 2, probability of retaining a false null. And the two things that go together with these. Probability of retaining a true null. If anyone's studying stats and knows what that's called, I don't know if it's got a name, I'm just calling it correct in blue. The probability of rejecting a false null has a very exciting name though. Power. Which, yeah, it's just the probability of rejecting a false null. Look, what might help you place these is if I kind of put them in columns and rows, see if this helps. Reality, the null is either true or not. We don't know. That's why we're doing research. But we've got to make a decision based on our sample mean. Are we going to retain the null and and conclude that nothing is happening? Or are we going to reject the null and say that something is happening? If the null is true and we retain it, that's correct. If the null is false and we reject it, that's correct, and that's power. The probability of that is power. If the null is true and we reject it, that's our type 1 error rate, which we can set at 5% because if our assumptions are correct, we understand the properties of the null sampling distribution. The probability of a type 2 error, well, we can estimate it if we have some estimate of the effect size, but often we can't really set it. We can't set it. We can set the type 1 error rate, we estimate type 2, and we estimate power. Something else that might help is you may have seen a matrix like this in another context of decision making. decision-making literature, maybe even clinical literature when you're doing diagnoses and things like that. The difference between a missing something that's happening, hitting something, you're correctly rejecting the null, you're correctly detecting the cancer, or a correct rejection or a false alarm. You think that something is happening when nothing is happening. If that helps you understand our little decision matrix here too, that's good too. Ultimately, in inferential stats, we're just making decisions. After all, this is a decision-making process I've been discussing up until now. Let's put these back onto the graphs and you can see them. The type 1 error, I've shown you before, the type 2 error. Notice how only two things are possible. Hang on, I'm going to skip back. If the null is true, you can only be correct and retain it. You can only be incorrect and reject it. So only those two. If the null is false, you can only incorrectly retain it or correctly reject it. So the null is true at the top here. You can correctly retain it or you can make an error and reject it. The null is false down the bottom, which means it's an error to retain it. And if you reject it, statistical power. So that's what it looks like when you graph it. From this point on, I'm interested in power. I'm going to focus on power. After all, power, the probability of correctly rejecting a null hypothesis that is false, boils down to the probability of finding something that we're looking for. So power's going to be the focus. Power is it's proportionate to everything else, but it's going to be something that I'm going to focus on. Again, it's just the probability of rejecting a false null. But to reframe it, it's the probability of finding an effect. So it's kind of important. We want to know what the probability is of finding an effect. Now, you'll see on the left there, factors affecting power. And this relates to one of the learning outcomes. Effect size. How can you visualize effect size? I mean, maybe don't look at that for a moment. Effect size is something I mentioned when it came to correlation. Is your drug having a barely perceptible effect, or is it having a huge effect? Is your therapy making people a little less anxious, or is it, virtually curing them? That's effect size. We see it graphically, now look at the graph, in terms of the distance between the hypothesized null mean of no effect, the top of this peak here, and the peak of the actual, effect, the actual distribution of what's actually happening over here. So I've got effect sizes there with the yellow arrows. You can see that when you're studying something that produces a medium effect size, power is much bigger than when you're studying something where it's a very small effect size. And that makes a lot of sense. The probability of you rejecting a null that's false when what you're doing in the study, what you're manipulating, is having a big effect, of course that probability is going to be higher. Another way of thinking about power, and this applies to all the factors affect power, amount of overlap. See how when you have a small effect size, there's this almost complete overlap between the hypothesized and actual distributions. But when you have a big effect size, there's less overlap in terms of the distributions. And if we move to a really big effect size, there's almost no overlap at all. And power is massive. So you'll see effect sizes estimated sometimes in the method sections of papers. In fact, I'll show you some examples in a moment. Effect size is really a really important factor for affecting power. There's nothing we have any control over, though. We're choosing to study something. Effect size is out there in reality. And if we're let me talk briefly about different effect sizes. Perception, if you want to study perception in psychology, you may have enjoyed Professor Bart Anderson's perception lectures in Psych 1002, or you should be looking forward to them because they're awesome. Perceptual effect sizes are often huge, particularly with powerful visual illusions. You only need a handful of participants and you can get effects immediately. If you're interested in language and studying language effects and how language systems works, bad news, the effect sizes are very small. You have to be very careful. have to be very clever in designing your studies. So different fields of psychology provide you with different effect sizes, with different amounts of power, different amounts of likelihood that you're going to find something. The variability of the effect is going to affect power. Now look at the curves now. The curves at the top are highly variable. And again, that little secret I told you earlier, the amount of overlap affects power. You can see it here too. Lots of overlap, less power. Very little overlap, more power. Now these are sampling distributions, but the variation of sample means in a sampling distribution is something called standard error, okay? Whereas standard deviation is the extent to which raw scores vary. Standard error, which if you want to think about it conceptually is just the standard deviation of sample means, that's the extent to which sample means vary in a sampling distribution. Now we estimate standard error by looking at standard deviation of raw scores, because if your raw score effects are highly variable and everyone who does your experiment gets a very different result, then not only are your raw scores going to be distributed widely, but your sample means are going to be very variable as well. So if your effect is variable, it's going to affect your sampling distribution. If your sampling distribution is highly variable, such that you would expect quite different sample means each time you run it, then you're going to have less power in a sense. So a variable effect at the top, a reliable effect at the bottom. When the effect is reliable, the sampling distributions are more tightly packed. There's less overlap in the distributions in that sense. Now, sample size. Although, let me go back a bit. I haven't forgotten to do the animation. When I move from variability of the effect to sample size, there's no change. And that's because the other factor that affects the variability of sampling distributions, other than the variability of the effect, is how many participants have you got. Now, this is hopefully fairly easy to understand. If you're running a study and it's only got 20 participants, I'll use the example I've got here, then sampling error is going to be quite high. Let's say your study is looking at reaction time. Well, if you randomly sample 20 people, the chance that, 12 of them have just had their morning coffee and, they're all jittery, that's quite plausible. Your next sample, if you were to simulate sampling again, it might be, and I suppose you can do this with your SONA studies if they're online. We know the data from undergraduate students. You guys are most active between 1 and 2 a.m. in the morning. Perhaps that's when you're watching this lesson. There's a possibility that your next sample is going to be doing your study at 1 a.m. in the morning, and they're going to be quite slow. When you've got a small sample size of 20, so your sample means are going to vary a lot. When you've got a sample size of 200 though, you'll still get people who have just had their morning coffee and people who are doing their study in the middle of the night, but with a sample size of 200, it's going to balance out. So a sample size of 200, less variability, less overlap, more power. And unlike all the other factors that affect power, we have most control over sample size. So that's kind of what we focus on in terms of manipulating power. We can only ever estimate power, but we estimate it mainly using, we need to take effect size into account, but it's sample size that we ultimately have control over. Effect size, variability of effect, sample size. And just to recap again, statistical power is the probability of rejecting a null hypothesis that is false. To express it more formally, it's the probability of finding an effect of a particular size given a particular sample size. So it can be expressed as a probability in this way, but as I said, it's only ever estimated. Here's some real examples from real research papers. You can see here Chan on the left has written, to achieve 85% power, 85% chance of rejecting a null hypothesis that's false, Each between subjects condition required 34 participants. Chan hasn't revealed his working there, but he's used software to find that out, and he's put that into his publication. Chan, yes, I know Chan. Chan was a reviewer on a paper I was involved with. To maximize power, this one on the right is from S. Gray Winkler. To maximize power, medium to large effects, they've mentioned the effect size, we targeted a minimum sample of 50 participants per cell. This is in the method section, talking about the sample. This is not in the results section. Another analysis, this is based on a sample size, so they're getting their sample size from prior research. This revealed that power was sufficient across all studies to detect a medium to large effect. Okay, so this might be unusual to you, but getting samples is expensive. I know you guys have to volunteer for, well, you don't have to, it's an opt-in type thing. You can do an assignment instead, but you opt in to do your 5 hours of research as part of your research participation. That is so valuable to researchers. The honours students, that helps. The postgraduate students, it is so valuable that you give your time to participate in research. So please pay careful attention when you're doing research. Another student's honours project may be on the line if you're not paying attention. But you know what? In the real world, participants are expensive. Look, even if they weren't expensive, we wouldn't want to be wasting your time for a SONA study if we didn't need you. So the honours students will be doing their equations and they'll be working out the power that they need. And so that they're not using more than they absolutely need, because you don't want to do that, because you'd be wasting people's time. If you could find your effects with 100 participants but you use 200, what are you doing? Well, you might think more is better, but I'll get onto that in a second. I want to catch everyone up at this point. I've shown a lot of graphs. It might seem a bit mathematical by this point, probabilities and numbers and so on. So I want to catch people up with the actual concept of statistical power before I go any further. Statistical power, another way of thinking of it, is sensitivity. Imagine that you're trying to find 3 objects: a beach ball, a tennis ball, and a marble. And they're different sizes, obviously. And I'm, in my little metaphor, the beach ball is the large effect size, the tennis ball is the medium effect size, the marble is the small effect size. And imagine that you're trying to find these objects with a telescope, okay? What's important to know is how far you are from the objects. And the distance from the objects here, I'm using as a metaphor for sample size. So imagine you have a very low power study, sample size is 10. I won't use the word power yet. You have a sample size of 10, which is as if you're very, very far away from these objects. In terms of the probability of detecting a large effect size, you have sufficient power in that sense. Because beach balls are quite large, they're colourful, even a kilometre away, you're probably going to be able to see it. Highly probable. But you're most likely fairly underpowered trying to detect a tennis ball. You're probably a kilometre, a tennis ball. There's a reason why they're yellow, but that's still very far away. And you're definitely not going to be able to see the marble. So underpowered for the others. You're only going to see the beach ball and nothing else. Bit closer, well, you're going to have sufficient power, sufficient sensitivity to see the beach ball and the tennis ball now. You're only 100 metres away using a telescope. Marble at that distance, I think I chose marble too because it's slightly see-through. Yeah, you're still going to be underpowered. You're not going to have the sensitivity in your setup to detect the marble. If you're right on it though, then yeah, you're going to be able to detect that marble if you're 10 metres away. Notice how the sample size is now 1,000 participants. If you were looking for a really small effect but you had 1,000 participants, you'd probably be able to find it. And you'd find all of the effects at that. But I just want to focus on the marble because, there's so many things in life, more is better. Well, I don't think that's true at all. I think we need to find a balance in all aspects of our life. This isn't a philosophy lecture. Just the right amount of food. Or you could do as Okinawans do when they eat and only eat till you're 70% full. The right amount of possessions, not too many, not too few. I don't want to get sidetracked. Anyway, more is better with sample size, isn't it? This is the naivety of young researchers learning about science. More is always better. No, it is possible to have too much power. Why would too much power be a problem? Well, if you have too many participants, too much power, then your study is too sensitive. And you would have seen this in the learning outcomes and thought, okay, we know statistical significance. We know statistical significance about the probability that the sample mean was drawn from a distribution where the null hypothesis is true. It's a statement of reliability and it's based on repeated sampling and so on and all kinds of assumptions. But practical significance is something different. A small effect, tiny effect size, which has no practical significance, may end up being ruled statistically significant. It's a problem. Here's a definition of the two. Statistical significance, and again, this is shorthand, this is not specifically correct, but it works well enough for first year. How likely the effect was due to chance or arose from a true underlying effect. Practical significance is how useful is the effect? Is it worth investigating further? Is it so small that it's kind of irrelevant and wasn't really the point of the research in the first place? Consider this example, which is from the Minium textbook, which is in your reading list. A link has been found between children's height and their IQ. Findings were highly statistically significant, okay, such that taller people have higher IQs. Wow, so that would make you feel pretty bad if you weren't that tall, and maybe make you feel good if you were tall. What was the sample size? Well, the sample size for this study was 14,000. What was the effect size? Well, the correlation between height and IQ was 0.02, which means you would not even be able to see that correlation on a scatter plot. And in practical terms means if for each additional IQ point of intelligence, you'd have to grow 4.2 meters. So the actual strength of the effect is, oh my God, it's a small effect. It's hard to imagine an effect. But when you've got 14,000 participants, it's like looking at something with a microscope. Your power is too great. Because your power is too great, you've found this relationship, which is so tiny and so practically insignificant, and it's irrelevant, and nevertheless, it's been statistically significant. It has been determined to be statistically significant. So too much power is a bad thing. You've really got to start thinking about effect sizes in your statistics. Statistical significance is one thing, but how important is this to me? These are called patient decision aids. I've got a source there at the top. This is no longer available, sadly. I don't know why they've gone out of fashion. They are so good. Many years ago, hormone replacement therapy was linked to breast cancer in women, obviously. And there was a worldwide panic. I think in the UK alone, 3 million women stopped taking hormone replacement therapy. If you're not sure what that is, it relieves so many of the symptoms of menopause. So many women around the world, millions, tens of millions, found relief in HRT. And yet this study was published, a 60% increase in breast cancer. There was no error in the study. The error was in the way the media reported it. The error was kind of in the 60% because this is a picture of 1,000 women. And of these 1,000 women, 10 women develop breast cancer because, it's tragically part of people's lives. You just develop breast cancer per se. But then in the sample of 1,000, 6 extra women developed breast cancer because they used HRT. It is a 60% increase, therefore. But when you step back and look at just what the actual additional probability is, there was no reason for a panic. And once decision aids like this were distributed to women around the world, to GPs, to medical practitioners, to show women, millions of women went straight back onto their HRT. Oh, okay, I read in the newspaper it was 60%. I started panicking, but now I understand. This is just beautiful. It's like a statistics lesson in a single image without needing a statistics lesson. This is another one I picked up. This one is live. If you want to follow the link's in the support documentation to save you typing that in. This is about the measles, mumps, and rubella vaccine. Something that's hotly debated. There are risks with taking every vaccine. There always are. But it's always got on the left there the risks of getting the disease you're being vaccinated against, and it can get pretty awful if you read that left column. I'd only critique this decision aid by saying it's not fair that the yellow in each is different. Things are yellow in the right. This is symptoms in kids. 4 of the kids might be irritable. I've been locked down. One of my family members has COVID at the moment. I've been locked down and the kids have been irritable constantly. Whereas it's ear infections and diarrhea is yellow on the left. So it's not a perfect decision aid, but these fields of people allow people who might not understand probability or percentages or statistics very well to see and make up their own minds. Unfortunately, this is the best present example I could find, and it's not very good. I think it's a step back from showing the individual people. This is about COVID vaccines. I think this is about, yes, it's got it on the top right. It's about the Pfizer vaccine, which I've had 3 times now. And it's got symptoms of people on the left who get COVID. And what have we got there? Symptoms 90 and 100, and they last for 2 to 3 weeks. There are symptoms on the right. You get, I had a rough day or two, and I got, I think it was my booster that caused the most trouble. You get symptoms from vaccines. They last 1 to 3 days. It's only 56 people in 100 at all. Possibly less. They might be nocebo effects. Not a big deal. The second row there, severe allergic reactions, 0, because they're talking about the COVID. And this is the bit I don't like, 5 in a million. Imagine drawing 5 in a million. I suppose it would be a teeny tiny dot across a whole page of people. It would be a bit hard to visually represent. But the problem with having this on a decision aid is people who don't understand stats and probability will see the 5 and instantly imagine themselves as one of the 5. Because it's the odds for winning the lottery are even lower than that, but people still buy lottery tickets after all. Hospitalisation, this is kind of where it's getting a bit better, where you can see it's 2.7 in 100,000 for people who get the Pfizer. I don't know how old this data is. You can look it up. Look up the link if you're interested in the latest data. But there on the left, 11,500 in 100, 10% of people who get COVID end up in hospitalisation. Thanks for clogging up our hospitals, vaccine deniers. Is it a good decision aid? Yeah, it's better than nothing, but I don't think it's as good as these fields of people. Here's another old example of fields of people. These have been used for political purposes. The only context I'm going to give you is for some bizarre reason, Australians don't seem to mind people who overstay their visas if they arrive by aircraft and just melt into the community, but we don't like people travelling by boat to our country. I think people who travel by boat to Australia because of its remoteness are friggin' the most courageous people on the planet, and we deserve to roll out red carpet, but we are spending millions of dollars on these brave people who come by boat. But these are kind of political frequency diagrams showing that, look, that tiny red dot there, that's what you're worried about, that you can barely see. Unbelievable. I think they're very effective, and I wish we had something like this for COVID vaccines to kind of show the true proportion of what is going on. If anyone's found one, send it to me and I'll stick it in the next version of the lesson. So understand the difference. So what I'm illustrating in all those, just to kind of get back on track, is effect sizes, trying to understand the practical significance of things. How useful is the effect? Is it worth investigating it further? Is it something that's going to have a big impact? Now, and just to go back somewhat on those examples, hormone replacement therapy, side effects of vaccines, you know what? Governments and people who run large public hospitals, they need to be aware, even if the numbers are tiny, because an extra blip on the tiny numbers might mean a requirement for a handful of extra hospital beds. But for the purposes of psychological research, when we're talking about teeny tiny insignificant effects, then it's probably not worth proceeding with them. If someone, for example, is arguing with you about acupuncture and you do a study with 100 participants and find nothing, and they say, well, do a study with 10,000 participants. Let's say you do a study on lower back pain with acupuncture with 10,000 participants, and finally you get this tiny effect size, then the person, again, driven by belief and confirmation bias, will say, see, I showed you it worked. But you can either politely or impolitely mumble and say, look, if it took 10,000 participants just to find something, it doesn't matter. You know, it's not worth charging someone $40 and taking up an hour of their time to give them that teeny tiny effect. It's not worth it. So people who say, oh, we need a bigger sample because we haven't we haven't resolved this issue yet, we need to keep studying all these strange things. Yeah, well, if you have to have a big sample, then it probably isn't worth investigating. It probably has no practical significance. It's not worth the money. It's not worth the time. So we've come a long way. Remember, we're just getting one sample mean per research study, and yet we're able to determine whether, what is the probability this sample mean came from a population where nothing was happening, and what is the probability this sample mean came from a population where a true effect occurred. And you can see why I put the little yellow M there, because if you think of the height of these lines as the probability, not probable, getting more probable as it gets higher, getting low, this is where the probability crosses for the null and the alternate distribution. This is our big region of uncertainty, where I think 0.05 is quite conservative. Science is quite conservative when you think about it, but you can see we're going to have not much power there because there's our cutoff. Always, when you're thinking about this, relate it back to the end of lesson 5, where I was talking about those two errors and the progress of science and how this is the challenge of inferential stats. Where do we go from saying, oh yes, 52 heads, not a big deal, to 70 heads, something's happening. And how do we do that mathematically and in a valid way? So this is how these things go together. Let me wrap up by talking about how science as a probabilistic decision-making system doesn't necessarily mesh well with human certainty or the desire for certainty. There's Voltaire there saying certainty is absurd, certainty is fanatical, certainty is essentially closed-mindedness. If you're really certain about something, you're essentially saying, I don't need to see anything else, I know. That's what certainty is. And yet people who don't understand science and demand certainty create all kinds of logical fallacies. I'm going to talk briefly about the appeal to ignorance. An assertion is thrust into a region of uncertainty. Well, all scientific conclusions are uncertain. There's no certainty in science. Here's the way it works. If your theory is not 100% certain, mine must be true. Can you see how that's a logical error? I'm going to attack your theory. If it's not perfect, then this theory over here, for which there's no evidence whatsoever, that must be true. Other variants you'll see, scientists are baffled. Because scientists don't know the absolute answer, anything goes, and all the other crap that has no evidence supporting it is true? No, that's an appeal to ignorance. The science is not settled. Tony Abbott, okay? What a bunch of rubbish. Overwhelming evidence. Yes, there are tiny percentages that this is not the case, but there are overwhelming percentages that it is. And are you really going to destroy your economy, your ecosystems, and the lives of millions in floods and fires and so on by holding out for certainty? Think of the person who waits for it to turn up 100 heads and even then says, no, it's probably a fair coin. That kind of ultra-conservatism causes real harm to the environment. It's just outrageous. And it's an example of the appeal to ignorance. Here's another example, which is supplied to us by, this is a really old show. When I was in second year uni back in 1995, I saw this live on television when it was brand new. That's how old I am. So you've probably never heard of it. Everyone looks really daggy. It's from a show called Friends, and Dr. Ross Geller is about to get cornered by someone called Phoebe as an example of appeal to ignorance. So have a look.
Uh-oh, it's Scary Scientist Man.
Okay, Phoebe, this is it. In this briefcase, I carry actual scientific facts. A briefcase of facts, if you will. Some of these fossils are over 200 million years old.
Okay, look, before you even start, I'm not denying evolution, okay? I'm just saying that it's one of the possibilities.
It's the only possibility, Phoebe.
Okay, Ross, could you just open your mind like this much? Okay? Now, wasn't there a time when the brightest minds in the world believed that the Earth was flat? And up until, 50 years ago, you all thought the atom was the smallest thing until you split it open and this, whole mess of crap came out. Now, are you telling me that you are so unbelievably arrogant that you can't admit that there's a teeny tiny possibility that you could be wrong about this?
There might be a teeny tiny possibility.
Can't believe you caved.
What?
You just abandoned your whole belief system. No, before I didn't agree with you, but at least I respected you.
But
How are you going to go into work tomorrow? How are you going to face the other science guys? How are you going to face yourself?
And then he just goes away. Okay, so what's happened there? First of all, Ross is a terrible scientist. I think this is established in the show. He doesn't understand science. He doesn't understand probabilities. But you know what? A lot of scientists don't. If you were looking for textbooks to assist with this lecture series, for example, I encourage you in the support notes to look for statistics for psychology or statistics for education or statistics for the behavioural sciences. We need to be good at statistics and understand probability in psychology and to a lesser extent biology because the data is messy. Physicists, paleontologists is a little less plausible, but physicists and chemists, nice clean experiments, data that is not variable. And that's where you get a lot of the arrogance, a lot of the misunderstanding that science is about certainties. What's most hilarious about this is that Phoebe just pokes this little hole and gets him to admit that there's a possibility, and that's the appeal to ignorance. She drives in, oh my God, you just collapsed and gave everything away. This is why I've got a picture of a house of cards. This is how the appeal to ignorance works, and it kind of, in its fullest, most dangerous form, it becomes something called denialism, where people assume that by just pulling one card out, everything's going to collapse. It's dangerous. It means it's certainty versus someone who's not certainty, and the certainty wins. It's a lot less funny, unfortunately, than the television example I showed you. Disease denial, for example. We're still trying to get a handle on cancer. We have cancer treatments, painful. They tragically don't always work, at least not for some cancers. And this allows the charlatans to come in and say, look, because you don't have a perfect understanding, I deny your theory of disease. I deny that this is what's causing cancer. I think it's crystal energy. And again, they think it's a house of cards. Holocaust denial. Some lunatic goes to Auschwitz, steals a rock from what is a sacred place, and that's illegal, takes it back to their grimy lab in their neo-Nazi fortress and says, oh, I can't find any Zyklon B in this pebble. The whole thing's made up. Oh my God, there is overwhelming evidence supporting most of our big theories, that we landed on the moon, for example, that climate change is happening. But because it's not absolutely certain, and not absolutely every single thing was videotaped, people, the nasty, illogical ones, kind of push things into the gaps. It's pathetic. It reveals a lack of understanding of science, that science is based on probabilities, not certainties. And it reveals all kinds of biases and racism and horror and wow. These dichotomies overlap, so have no fear in an exam. I'm not going to put in more than one in the same place. False, because you can see they overlap. Appeal to ignorance relates to denialism. False dichotomy is another one where you make out that there are only two perspectives, that there are only two answers. And instead of adequately supporting your own position, you just attack the other one. Okay, evolution denial's a good thing. There's no evidence that, things were created or anything like that, but we won't bother about that. We're just going to attack the theory of natural selection, which is very hard to attack because it's such a powerfully supported theory. The microbiology and the DNA evidence supporting it is astonishing, and sadly something we're coming to terms with now as the coronavirus evolves. But yeah, there's no mention of supporting their view. It's just, let's attack this one. Let's find a tiny gap. Oh my God, it's all made up. Therefore, our bizarre metaphysical account is correct. That's false dichotomy. And it comes up here too. I just want to focus on climate change. This is a false dichotomy, excluded middle type situation where, and this happens a lot in the media too, but definitely in politics, we've got very black and white sides. It's either completely made up, so says the Murdoch press and the Australian, or it's catastrophic. I suspect a lot of politicians saying it's catastrophic are doing so to try and counterbalance that. But it's not helpful, because a real scientific debate is probability-based. What's the probability these kinds of things are going to happen? Give us some probability curves, okay? Are we talking 2 degrees by this year, 3 degrees? What's the sea level rise going to be like? These terrible bushfires, these terrible floods. Let's talk about probabilities, not this hysterical political, it's either happening and it's terrible or it's completely made up. That's not what science does. Science is a probabilistic decision-making system. The best one we have right now. It's been a pleasure attempting to explain it to you. Head over now to the second and final workshop, have a go at the questions. And if you have any questions for me, you can ask them before the workshop or during the workshop, because that's it for the lessons. I hope you enjoyed them.